Hello folks, I'm Mr. Pinola. In front of me today is a simple circuit. You'll notice I have a voltage source made up of 4 batteries. I have a light bulb in a holder, and I have a switch. Right now the switch is open, which means that no electrons are flowing through my circuit, and there's no current, and obviously the bulb is not lit up. Let me close the switch and we should see the bulb light. That's indeed the case. The bulb lights up and it appears very bright because it is getting all 6 volts from the battery. If I open up the switch, it obviously turns the light off. Now, with my switch remaining open, I'm going to remove the light bulb from the circuit. And I'm just going to take these 2 alligator clips and I'm just going to connect them together. Do you see a problem right now with this circuit? Do you see a reason why I should not close the switch? I hope you do. And that's because something is missing from this circuit. Do you know what it is? There's no resistance. And if there is no resistance in a circuit, then electrons can flow as fast as they want. Now, I guess technically there's a little bit of resistance in the wires because they're long and very thin. So there's a little bit of resistance there. But still, there is very little resistance, which means there's probably going to be a very high current. And that can be extremely dangerous. Do you know what it's called when there is basically no resistance and therefore the current is almost to infinity? That's called a short circuit. And that's what I would have going on here if I was to close the switch. I'm not going to do that because that could create a potentially very dangerous situation. But today, we'll talk about ways that we can deal with using electricity safely and making sure that we are protected when using electrical devices. So it's very clear that something needs to go in this gap in my circuit for when I close the switch. Otherwise, the current would be almost to infinity, and I could risk creating a serious electrical hazard. Now, we know I could put a light bulb in this gap because light bulbs have resistance. I could also put a resistor in this gap because a resistor would also provide resistance. However, a lot of times people will like to use devices that will make sure that they are safe in conjunction with an electrical circuit. This device that you see here is called a fuse. F-U-S-E, a fuse. Fuses are put in circuits because they prevent the current from getting too high. This particular fuse is labeled as a 2-amp fuse. That means that if the current in the circuit in which the fuse is hooked up to goes above that amount, the little piece inside the fuse will melt and it will shut down the entire circuit. When the fuse melts, it opens up the circuit just like a switch popping open, and it stops any more current from flowing. Now, most of the time, electricians will put fuses in circuits along with other elements to make sure that the current doesn't get above a certain amount. Here, we know the current is getting above a certain amount. We're just going to use this to show how the fuse actually works. So let's put the fuse carefully into my circuit. I'm just going to hook it in here with a couple alligator clips. And then I'm going to close my switch, and we should see the fuse burn. In fact, what you might notice is a little bit of a spark coming as the fuse melts inside and opens up the circuit. Let me turn off our lights before we observe what a fuse does. So my lights are completely off and I have my fuse hooked up to the circuit. We know that there's no or very little resistance in here, so the fuse should definitely burn out. The current is definitely going to go above 2 amps. So let's close our switch and let's keep our eyes on the fuse. I know you can't see it right now, but you should see it light up when it melts. 3, 2, 1. Did you see that? The fuse melted. What you're looking at right now is a fuse that has not burned out. Notice how there is a piece of metal that goes straight across? That's because the fuse is designed to be a conductor when there is a low enough amount of current in the circuit. Let me show you the fuse that I just hooked up that you saw melt in that particular circuit. Do you notice how this fuse is a little bit bowed, and also it stops here? It's melted and it is no longer a single continuous piece of metal. That means that this fuse will not conduct electricity anymore because the fuse has burned out. It's melted. It shuts down the circuit, and it did so because the current was too high. Thank goodness, or we could have risked having a short circuit and burning our battery out. Welcome back to my lab setup, which contains my burned out fuse. This fuse sensed that there was too high a current, and so it melted. And right now, no current can pass through the circuit. What can we do to get current flowing again? Well, we physically have to go into the wiring, remove the fuse, and then do one of two things. If we think the problem has been fixed, we can replace the fuse with another one that has a little bit of a higher tolerance. This fuse, for example, goes up to 20 amps. That means it can handle much more current, and it will only burn out if the current goes above 20 amps. There's a lot more flexibility with a fuse like this. But that can be very dangerous because if we haven't fixed the problem, the current can still get dangerously high. That's why a lot of times if a fuse burns out, the electrician needs to address the issue and then needs to go back into the wiring and insert a new fuse directly into the circuit. That can be quite annoying to do, to have to constantly go into the nuts and bolts of the wiring and physically replace the fuse. Wouldn't it be much easier if, rather than a fuse, our switch simply knew when to pop open? Then, if the current got too high, the switch would automatically know, all right, current is too much, let me pop open. Then if there's an issue, we could fix it and just reset the switch just by pushing it down. This would be a lot easier to handle than having to go in and replace the fuse. And that is exactly the job of a circuit breaker. A circuit breaker performs the same function as a fuse, except it is basically like a switch, which is much easier to reset. Here's a picture of many circuit breakers. In fact, you might have an electrical box containing circuit breakers like this at your house. I bet you probably do. You can see that the person on here is resetting their circuit breaker. Chances are, the circuit breaker had sensed that current was too high in a certain area and tripped, meaning that it shut off. If the person has addressed the electrical issue and they're satisfied with it, they can just reset the circuit breaker by flipping it on again. Circuit breakers are much easier to reset than fuses, and they perform essentially the same function. There are many other electrical safeties in your house. For example, here is an outlet on the screen. You likely have many outlets like this at your house. And you might notice that there are 3 places for prongs when you use the outlet. There are those 2 small lines that almost look like eyes, and then there's that little opening in the middle that almost looks like a mouth. However, you may have noticed that some devices do not use all of those openings. Let me show you. Here is a device which has a plug that only has 2 prongs. This is the charger for my Chromebook, the laptop that I use. Since it only has 2 prongs, that means it's missing the 3rd prong. But what is the function of the 3rd prong? Well, let me bring in a device that does have that 3rd prong. I'm going to shift my camera a little bit. You'll notice that I've brought my microwave, which has made some other appearances in my video, into the picture. Here is the plug for the microwave, and if you look closely at it, you will see that there are 3 prongs on the microwave. There are 2 prongs here, and there's also a third one that comes down in the middle. The microwave would fit into all of the openings of that outlet. To understand the importance of the third prong for our electrical outlets, I have to tell you a little bit of a story. A few years ago, I had a very old lamp, and the lamp had 2 prongs, just like my Chromebook charger. I had the lamp plugged into the wall, and I decided I was going to move the lamp. So I turned it off, and then I went to go unplug it with my hand. Even though the lamp was off, when I went to go unplug it, I got a shock. And I wondered why that is, even though I had already unplugged the lamp. And that's because there were some extra charges, some extra electrons that were still residing around the plug. When I touched it, those extra electrons went into my body and traveled through my body into the ground, which could have been a very dangerous thing. If the lamp had had a third prong, that's where the electrons would have gone. They would have traveled in through the third prong and then into the ground. That's a process that's called grounding. Grounding is the removal of excess or extra charge. If you have a device that has a couple extra electrons hanging around on it and you ground it, you will take those extra electrons and deposit them into the ground. That's very helpful because then the outlet or your device is back to neutral and is safe to touch. So when you're using an electrical device, look for that third prong. If it's there, then you know the device is grounded when it's plugged into an outlet like this. And when you turn it off, there won't be any excess electrons hanging out that could potentially shock you. That's why it's always really safe to make sure that you use that third prong. It is there for grounding purposes. So here's a side-by-side picture showing you an ungrounded outlet and a grounded outlet. You will notice this is a clear image of the third prong, and this device that has the third prong would be much safer to use because the grounding plug will remove any excess electrons or any extra charge that may be residing after the device is turned off. Now, I'm going to stop sharing my screen with you, and I'm going to show you a device that I have here. This is an outlet that you might see in a home. Do you notice something different between this and the outlet I was just showing you on the screen? Well, there are a couple of differences. First off, this outlet has these buttons in the middle, and you may also notice this small little light that can go on. This is not a standard outlet. This is called a GFCI, and I'll write those letters on the board. A GFCI stands for a ground fault circuit interrupter. And although it might look like a regular outlet, it performs a very specific function, which is different from a circuit breaker and a fuse, but still helps keep us safe. So let's explore what a ground fault circuit interrupter does. To understand that, let's look at the last word, interrupter. What does it mean to interrupt someone? Well, that means the person is speaking and you say something in the middle of them speaking. You have interrupted them. And usually that's a very rude thing to do because it's almost like you're saying whatever you are talking about is more important than what they're saying. Well, We would want somebody to interrupt us if they had something extremely important to say. For example, if there was a fire, I would want somebody interrupting me, telling me that there's a fire and I need to get out of the building. That's exactly what a ground fault circuit interrupter does, except it doesn't alert us to fires. Instead, it alerts us to something potentially very dangerous, and usually in areas with a lot of moisture. It alerts us to unequal currents. And let me show you why those are very dangerous things. Action 1. So let's imagine that I have an electrical device. And that device is operated with electricity. So let's say that the current going into that device is 3 amps. How much current should be going out of that device back into the wall? If you said 3 amps, you'd be right. That's because of the law of conservation of charge. If we have charge coming in, that charge must leave, part of a closed circuit. If 3 amps come in, we know that we're safe if 3 amps go back out. But what if only 2 amps go back out? What happened to the extra 1 amp of current? Well, it could have gone somewhere else. And that's a potentially very dangerous thing. If the ground fault circuit interrupter notices that the incoming current and the outgoing current are not equal, or that there are unequal currents, it will shut down the entire circuit. And you will have to reset it after you remedy the problem. The ground fault circuit interrupter does not shut down a circuit if current is too high. It is a special device that shuts down current if the current going in and the current going back out are unequal, because chances are the current that's missing has potentially gone somewhere dangerous. Now, you might notice from the story that I told you earlier, or perhaps from your experience, that there are many people who are alive today who have experienced electrical shocks. And you might say, how is that possible if electricity flows through their body? Well, the issue is that it is the current that kills us, not the voltage. And if you recall Ohm's law, current, or I, is equal to V divided by R. You're told to stay away from high voltage sources, like outlets in your home or high voltage power lines, because that could create a very large voltage. And as a result, if voltage is high, there will be a lot of current. But thankfully, and again, please don't try any of this at home, thankfully, our bodies have a lot of resistance. So, as long as the current is not too high, in some cases, we might be okay even if exposed to large voltages, if our body has enough resistance. Because if resistance is high, then current is low. So, chances are, if you were somebody who has experienced an electric shock in your life, you were okay thanks to your body's resistance, which brought down the current to a safe level. Action 1. So we just showed that you are sometimes protected from electric shocks if there is enough resistance in your body. But what if the resistance in your body was very low? Well, that would cause the current through your body to be very high. And that could potentially create a deadly situation. But how does our body's resistance change? Well, there is one very common thing that lowers our body's resistance. And you might have noticed I picked up a blue marker to show you. That's because if our body is wet, maybe if we just came out of a pool or out of the bathtub and we go to operate electricity, we would have lower resistance because of the presence of moisture on our body. This is why it's so dangerous to use electricity around water, and you should never do it. That's because water lowers your body's resistance when you're wet, and thus creates much higher electric current. Lower resistance, higher current, and that could become much more dangerous for you if you experience an electric shock and expose yourself to a potential difference or a voltage. If there's anything that you understood from this unit, have it be electrical safety. It's really important to be safe around electricity. That's why people often install things like fuses when they're wiring their homes. Fuses can melt when the current gets too high. Circuit breakers, as we saw, operate very similarly to fuses, except instead of melting, they are just a fancy switch that pops open when the current gets too high. We also discussed today about how grounding, and specifically the third prong on certain outlets, can help keep us safe, because it will get rid of any extra charge and bring it to the ground. We also saw GFCIs, the type of outlet that I showed you, which don't shut down the circuit when the current is too high, but do shut down the circuit when the current going in and the current going out are unequal, because current might be leaking off somewhere. And finally, we saw that being wet and around electricity is a potentially very dangerous combination. That's because if you have a lot of moisture or a lot of water on your body, your resistance will be lower and it'll be much easier for current to flow through you, which can be a very bad thing. I hope you learned something about electrical safety today. There can be a lot of benefits to using electricity, but we must make sure we do it responsibly and safely. Thanks for watching today.